Modern medical care moves at high speed, but the data required is overwhelmingly transported in physical folders, printed pages, and manual handoffs. Consider a specific diagnostic pathway: an older male patient presenting with severe symptoms on day 0. By day 8, his medical team achieves a complete, complex staging picture for invasive adenocarcinoma. From a purely medical standpoint, the execution across 3 separate facilities is flawless. The clinical velocity and the diagnostic judgment are sound. This diagram tracks the timeline. You see a swift progression from day 0 symptom presentation to day 8 staging completion across an anatomic pathology lab, an imaging center, and a cytopathology unit. The handoffs between the gastroenterologist, radiologist, and oncologist happen exactly as they should. Yet beneath this clinical success, the underlying information architecture is in a state of total collapse. Over these 8 days, 14 distinct decision-makers interact with this patient's case. 0 of them write their findings into a shared digital record. The entire multi-facility pathway functions only because the patient physically carries printed documents from one disconnected organization to the next. The patient is acting as the integration bus. Applying surface-level digital tools to a system like this does not eliminate risk, it scales it. To fix this, we need to examine the trap of pseudo-contactless sharing, expose the structural threats of dark and phantom data, and build a 3-dimensional integration fabric. When health systems attempt to digitize a fragmented estate, they frequently mistake operational convenience for actual semantic integration. They replace the paper, but they do not resolve the data. This matrix evaluates data transfer methods based on 2 variables: the speed of the transfer on the x-axis and the strictness of data custody and governance on the y-axis. Quadrant 3 represents the traditional in-contact method. A patient carrying a paper record introduces high friction and delays, but the physical nature of paper creates a naturally bounded chain of custody. Quadrant 4 is the pseudo-contactless trap. This occurs when hospitals email PDF reports or families send medical records via consumer apps like WhatsApp. The latency drops to near 0, but custody and governance drop to exactly 0. This exposes the inverse friction law of health IT. In a fragmented system, the least governed communication channel is always the most capable and widely used. Quadrant 4 creates unique dangers. A physical piece of paper can only be lost once. A PDF sent over a messaging app creates infinite, untrackable copies of protected health information resting on servers across the globe. Removing physical contact without adding digital provenance leaves clinical data in an ungoverned and unauditable state. We can observe exactly how that abandonment jeopardizes care by returning to the 8-day pathway. Relying on unstructured, narrative PDFs breeds 2 specific, life-threatening architectural pathologies. The first is phantom data. This occurs when conflicting information exists in the medical record, but the system implicitly trusts both values because it lacks the capacity to reconcile them. On day 6 of the patient's timeline, 2 separate imaging reports, a PET CT and a pelvic MRI, are generated hours apart at the same facility. Looking at these 2 reports side by side, the PET CT measures the primary lesion's wall thickness at 1.3 centimeters. The MRI measures the exact same lesion at 7 millimeters. Because these reports are saved as 2-dimensional text blobs, the IT system files them side by side without firing a single alert. The treating oncologist is left with an ambiguous, unreconciled baseline to measure future treatment response. The second pathology is dark data, critical clinical inputs that are documented as text but never structurally tracked or executed. Notice this footnote at the bottom of the Day 3 pathology report. The pathologist explicitly advises molecular reflex testing to determine if the patient is eligible for immunotherapy. Because narrative advisory text cannot trigger a discrete, trackable order in the hospital software, the recommendation becomes dark data. By day 8, this stage-defining clinical loop remains permanently unresolved. Healthcare IT already possesses the capability to perfectly structure and track discrete data across organizational boundaries. It does this every day for billing and revenue cycles, utilizing the same strict semantic governance found in the banking industry's settlement infrastructure. To eliminate dark and phantom data, we must point that existing structural rigor toward clinical care. We do this by climbing the document AI extraction ladder. This diagram illustrates that ladder. Basic 2D optical character recognition simply digitizes the fog. True clinical safety requires moving to 2.5D semantic coding, where raw text is bound to standardized medical vocabularies, and ultimately up to 3D integrated extraction. 3D extraction resolves data along the provenance axis. It relies on an enterprise master patient index to guarantee information is linked to a specific human identity across facility boundaries. Those conflicting 1.3 centimeter and 7 millimeter measurements are pulled from the text, converted to standardized units, and merged into a single queryable data object. The clinical payoff is immediate. When a canonical lesion registry detects two divergent observations of the exact same tumor, an automated concordance rules engine instantly fires an alert to the multidisciplinary team. Simultaneously, a reflex order engine reads the Day 3 pathology diagnosis and auto-generates discrete, trackable requests, ensuring those critical molecular tests are actually completed. 3D extraction transforms passive PDFs into an active integration fabric, allowing automated rules to detect phantom and dark data before they reach the clinician. Securing this architecture requires addressing a final misconception: the belief that the only alternative to fragmented data silos is creating massive, centralized data pools. This network topology map shows why centralized pooling is a national security and privacy vulnerability. The correct architecture relies on a federation layer. The central hub contains only identity pointers and indexes, while the actual medical data remains securely held in the edge systems. This enables a compute-to-data model. Extraction algorithms travel to the edge, but clinical payloads never leave the hospital's custody. Because edge systems enforce purpose-of-use gateways, the architecture physically blocks unauthorized access, creating a structural fence against actuarial functions. Beyond the technical specifications, the ultimate measure of clinical data architecture is human compassion. In our initial 8-day pathway, a confirmed malignant diagnosis sat finalized in a database for 72 hours before the decision-maker who needed it was actually aware it existed. A compassionate data architecture is measured by a single metric: latency to truth. Shifting from unstructured PDF payloads to a federated integration fabric cuts this latency from days to hours. It ensures the architecture tells the patient what it knows, in time, and entirely on their terms.